The fabric of reality, Einstein's universe unveiled. A curious mind and a radical idea. Imagine the year 1905, a veritable annus mirabilis for a young, unassuming patent clerk in Bern, Switzerland. His name was Albert Einstein, and in that single year, he published 4 groundbreaking papers that would utterly reshape our understanding of the universe. This book is primarily about one of those revolutionary ideas, the theory of relativity. Forget what you think you know about space and time, because Einstein proved they are not what they seem. They are not fixed, immutable backdrops against which events unfold, but dynamic, interwoven elements that twist and warp in ways previously unimagined. His work didn't just add a few new equations to physics, it fundamentally changed our perception of reality itself. Before Einstein, the universe was a stately clockwork mechanism, governed by the precise, absolute laws laid down by Isaac Newton centuries earlier. Space was a rigid, unchanging stage. Time flowed uniformly for everyone, everywhere. Gravity was a mysterious, instantaneous force pulling objects together across vast distances. It was a comforting, intuitive picture of reality. But not for Einstein. He possessed a rare blend of deep intuition, relentless curiosity, and a willingness to challenge the most deeply held assumptions. He didn't just question the answers, he questioned the questions themselves. Legend has it, even as a teenager, he pondered what it would be like to ride on a beam of light. Such seemingly simple thought experiments led him down a path that would dismantle the Newtonian edifice and reconstruct a universe far more intricate, more surprising, and infinitely more fascinating. Relativity sounds complex, even intimidating. Images of blackboards filled with indecipherable equations and paradoxes involving twins and spaceships often come to mind. But at its heart, relativity is about something very simple: how observers measure things, and how those measurements depend on their motion relative to what they're observing. It's about perspective, yes, but a perspective rooted in ironclad principles. In the coming chapters, we will embark on a journey that will reveal why the speed of light is the ultimate cosmic speed limit, how time can literally speed up or slow down for different observers, why objects can appear to shrink when moving at astonishing speeds, the astonishing truth behind the universe's most famous equation, E equals mc2, how space and time are inextricably linked into a unified spacetime fabric, why gravity isn't a force, but a profound curvature in that very fabric, the existence of mind-bending phenomena like black holes, where the rules of physics break down, how Einstein's ideas shaped our understanding of the Big Bang and the origins of the cosmos, even how his theories are vital for technologies we use every day, like your GPS navigation system. This book is for curious minds, for anyone who has ever looked up at the stars and wondered, what is reality, really? We will use thought experiments, vivid analogies, and historical anecdotes to make these concepts clear, without relying on complex mathematics. So, prepare to have your mind stretched and your understanding of the universe profoundly expanded. The journey begins with a young man's radical idea and a universe waiting to be unveiled. Newton's clockwork universe. For over 2 centuries before Albert Einstein emerged on the scene, the universe was largely considered to be Isaac Newton's domain. Born in 1642, the very year Galileo Galilei died, Newton bequeathed to humanity a vision of the cosmos that was as revolutionary as it was elegant. His monumental work, Principia Mathematica, published in 1687, laid down the laws of motion and universal gravitation that underpinned science and engineering for generations. Imagine the universe as a magnificent, perfectly crafted clockwork machine. Newton's laws described this machine with breathtaking precision: absolute space. For Newton, space was a fixed, unchanging, three-dimensional stage upon which all events unfolded. It was like an invisible, immovable grid, providing a universal reference point for motion. Whether you were sitting still or hurtling through the cosmos, your position and movement always related to this absolute background. Absolute time. Similarly, time was an unstoppable, unvarying river flowing uniformly for everyone, everywhere. A second was a second, whether measured on Earth or on the most distant star. Clocks ticked at the same rate, regardless of who was watching them or how fast they were moving. There was a universally agreed upon, now, gravity as a force. Newton unified the heavens and the earth by showing that the same force that pulled an apple from a tree also kept the moon in orbit around the earth and the planets around the sun. This force, gravity, was an invisible pull between any two objects with mass. It was thought to act instantaneously across any distance, a concept that even Newton himself found somewhat mysterious but undeniably effective in his equations. This Newtonian framework allowed scientists to predict the orbits of planets with astonishing accuracy, design sturdy bridges, explain the rhythm of the tides, and even calculate the trajectory of cannonballs. It propelled the Industrial Revolution and became the bedrock of physics, taught in schools and universities worldwide. It was intuitive. If you were on a train moving at 50 miles per hour and you walked towards the front at 3 miles per hour, your speed relative to the ground was simply 53 miles per hour. If you walked towards the back, it was 47 miles per hour. This simple addition and subtraction of velocities, known as Galilean relativity, made perfect common sense. However, even as Newton's mechanics reigned supreme, new discoveries began to emerge that hinted at a deeper, more complicated reality. In the mid-19th century, Scottish physicist James Clerk Maxwell achieved another triumph of unification. He brought together electricity and magnetism into a single, elegant theory, expressed through his famous set of 4 equations. These Maxwell's equations didn't just describe electric and magnetic fields. They predicted the existence of electromagnetic waves, light itself, and, crucially, predicted their speed. According to Maxwell, light should always travel at a constant speed in a vacuum, approximately 186,282 miles per second, or about 300,000 kilometers per second. This was an extraordinary prediction, but it immediately begged a crucial question: constant relative to what? If a train observer measured the speed of light and a stationary observer measured the speed of light, would they both get the same answer? In the Newtonian universe, this seemed impossible. If light was a wave, like sound waves traveling through air or water waves through water, then it must be traveling through some medium. This hypothetical medium was christened the luminiferous ether, an invisible, massless, perfectly transparent substance that was believed to fill all of space. Scientists imagined Earth moving through this ether, much like a boat moving through water. If this were true, then light speed should appear different depending on whether you were moving with the ether, against it, or perpendicular to it. Just as the speed of sound depends on your motion relative to the air, so too should the speed of light depend on your motion relative to the ether. This was the quiet, simmering problem at the heart of classical physics. It was a problem that would ultimately lead to some of the most famous experiments in scientific history and set the stage for Einstein's daring intellectual leap. The clockwork universe, so precise and predictable, was about to encounter an unexpected flaw in its machinery, one that would unravel the very fabric of space and time. The cosmic speed limit. The stage was set. Isaac Newton had given us a universe with absolute space, absolute time, and gravity as an instantaneous force acting across distances. James Clerk Maxwell had given us light as an electromagnetic wave traveling at a constant, astonishing speed. A speed that seemed to defy the simple addition of velocities that worked so perfectly for everything else. To reconcile these seemingly conflicting ideas, the luminiferous ether was conceived, an invisible, pervasive medium that was believed to fill all of space, through which light waves propagated. Scientists felt certain that if they could detect this ether, they could solidify the foundations of physics. They reasoned that if Earth was hurtling through space at a tremendous velocity in its orbit around the Sun, then it must be moving through this stationary ether. This journey would create an ether wind. Much like standing on a moving train creates a wind even on a calm day. If light traveled through this ether, then its measured speed should change depending on whether it was traveling with, against, or across this ether wind. This theoretical ether wind was the quarry for 2 brilliant American physicists, Albert Michelson and Edward Morley. In the late 1880s, they designed one of the most ingenious and precisely executed experiments in scientific history, one explicitly intended to measure this elusive ether wind. Imagine their setup, known as an interferometer. It begins with a single beam of light, which is then split into two identical beams using a partially silvered mirror. These two beams are sent off in perpendicular directions, each traveling to a mirror and reflecting back. When the two beams eventually recombine at a detector, they create an interference pattern, a series of light and dark fringes. Because the light waves, having traveled slightly different paths, might be slightly out of sync. The genius of the experiment lay in its extreme sensitivity. If an ether wind existed, then one of the light beams traveling against or with the wind would take a slightly different amount of time to complete its journey than the beam traveling across the wind. This tiny difference in travel time, even infinitesimally small, would cause a shift in the interference pattern observed at the detector. It's a bit like two swimmers in a river, one swimming upstream and back, the other swimming across the river and back to the starting point. Even if they swim at the same speed relative to the water, the one swimming upstream and back will take longer if there's a current slowing their progress against it. The same logic should apply to light moving through the ether. Michelson and Morley carefully rotated their entire apparatus, mounted on a massive stone slab floating in mercury to minimize vibrations, to detect any change in the fringes as Earth's motion through the supposed ether shifted its orientation. They performed the experiment repeatedly, at different times of the day, and at different times of the year, expecting to see a clear, measurable shift in the interference pattern, definitive proof of the ether wind. But to their astonishment, they found nothing. Absolutely no shift. The interference pattern remained stubbornly the same, regardless of how the apparatus was oriented or how fast Earth was supposedly moving through the ether. It was a perplexing and deeply troubling result, a null result that baffled the scientific community. This result meant that either there was no ether for light to travel through, or Earth was always at rest relative to the ether, which was entirely implausible, given its known movement around the sun, or something fundamental was profoundly wrong with their understanding of light and motion. The Michelson-Morley experiment created a full-blown crisis in physics. The seemingly simple and intuitive Newtonian world, where speeds could be added and subtracted at will, couldn't account for this stubborn fact. The speed of light simply did not change, no matter how fast the observer was moving or in what direction they were moving relative to the light source. It behaved like no other wave. It traveled at the cosmic speed limit, a constant for everyone, all the time. This was the profound puzzle staring scientists in the face at the turn of the 20th century. Old theories were crumbling, and ingenious, often convoluted, attempts were made to patch them up. Some suggested that objects contracted in their direction of motion, or that clocks slowed down when moving through the ether, but these were ad hoc solutions, lacking a unifying principle or elegant explanation. It took the bold, imaginative genius of a young Albert Einstein to look at this crisis, accept the puzzling result of Michelson and Morley, and instead of trying to explain it away with complex mechanisms, he embraced its implications fully. He realized that the problem wasn't with the experiment, but with the very assumptions about space and time that everyone had taken for granted. His solution would be breathtakingly simple in its premise, but revolutionary in its consequences. The stage was now truly set for special relativity. Special relativity, the two unshakable truths. The Michelson-Morley experiment had delivered its stunning, silent verdict. Ether, if it existed, was undetectable. The speed of light stubbornly refused to change, no matter how fast or in what direction the observer was moving. This was the precipice of a scientific crisis, a chasm between the elegant edifice of Newtonian mechanics and the equally elegant, yet contradictory, observations of light. Many physicists tried to patch up the old theories, proposing complicated mechanisms for contraction or slowing down. But Albert Einstein, in his profound genius, took a different approach. Instead of trying to explain away the strange behavior of light, he embraced it. He didn't see the Michelson-Morley result as a problem to be solved within the old framework, but as a fundamental clue to a new and deeper reality. He made a radical leap, proposing two deceptively simple postulates that would, when taken together, dismantle the Newtonian universe and construct an entirely new one. Postulate 1. The principle of relativity. The laws of physics are the same for all observers in uniform motion. What does uniform motion mean? It refers to what physicists call an inertial frame of reference. Imagine you are on a train moving at a constant speed along a perfectly straight track. If the train is moving smoothly, with no acceleration, no jerks, no bumps, then any physics experiment you conduct inside that train, say, dropping a ball or throwing a baseball, will yield the exact same results as if you were performing the same experiment on solid ground. You wouldn't know you were moving unless you looked out the window. This idea, that the laws of mechanics are the same in all inertial frames, was actually an old concept, going back to Galileo. Einstein's radical extension was that this principle applies not just to mechanical laws, like the motion of thrown objects, but to all laws of physics, including the laws of electromagnetism and light. This meant that Maxwell's equations, which described light, must also be the same for everyone in uniform motion. There is no preferred, absolute state of rest. No perfect reference frame for light, no ether. Your moving train is just as valid a frame of reference as the Earth, or the Sun, or a distant galaxy. Postulate 2. The constancy of the speed of light. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the source or the observer. This is the postulate that directly addresses the Michelson-Morley experiment and profoundly challenges our everyday intuition. Let's revisit our train example, but this time, instead of throwing a ball, imagine you shine a flashlight down the aisle. If you're traveling at, say, 60 miles per hour and the light leaves the flashlight, you would intuitively expect its speed relative to a person standing on the embankment to be 60 miles per hour plus the speed of light. After all, that's how velocity's added for balls and trains in Newton's world. But Einstein's second postulate, a direct consequence of the Michelson-Morley result, says this is not what happens. No matter how fast you, the flashlight, or the train are moving, both you on the train and the person on the embankment will measure the light leaving the flashlight at precisely the same speed. 186,282 miles per second, the speed of light, denoted as c. This applies even if you were shining the flashlight backwards on the train. The speed would still be c for both observers. Think about how utterly bizarre this is. If you send a beam of light past a friend who is zooming by in a spaceship at half the speed of light, both you and your friend will measure the light beam moving at the exact same speed. It doesn't matter who is moving or how fast, the speed of light remains an absolute constant. This is the cosmic speed limit, and nothing can exceed it. These two postulates, simple in their statement but profound in their consequences, are the foundation of what we call special relativity. Special implies that it only applies to observations made in inertial frames, that is, frames that are not accelerating. We'll deal with acceleration and gravity later, with general relativity. At first glance, these two statements seem contradictory, especially when you try to apply your everyday experiences with speed and motion to them. If the laws of physics are the same for everyone, and the speed of light is always measured as c for everyone, then something fundamental about our understanding of space and time must change. The only way these two postulates can both be true is if space and time themselves are not absolute and fixed, as Newton believed, but are relative and malleable. Time must literally slow down, and distances must shorten, for moving observers in such a way that both observers agree on the speed of light. Einstein didn't invent time travel or make spaceships disappear. He looked at the available evidence, made two bold and elegant assertions, and then logically deduced the astonishing consequences. The universe, he showed, was far more dynamic and interconnected than anyone had ever imagined. The next chapter will explore these astonishing consequences: time travelers and shrinking spaceships, Einstein's two postulates for special relativity, that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is constant for all such observers, might sound innocuous, almost obvious. But when you take them together, as Einstein did, they demand a radical reevaluation of our most fundamental concepts: space and time. If the speed of light is an unshakable constant, then time and space themselves must be flexible, altering their dimensions depending on an observer's motion to make that constancy hold true. This leads to some astonishing and counterintuitive consequences, which have been repeatedly confirmed by experiment. The most famous of these is time dilation, the idea that moving clocks run slow. Imagine a simple clock, an Einstein clock. It consists of two mirrors with a light pulse bouncing vertically between them. Each tick of the clock is one round trip of the light pulse, say, from the bottom mirror to the top and back down again. If this clock is stationary next to you, the light travels a direct, vertical path. Now, imagine this same light clock is on a rapidly moving spaceship, passing by you. From your perspective, standing still on the ground, the light pulse inside the spaceship's clock doesn't just go straight up and down. Because the spaceship is moving horizontally, the light pulse must travel a diagonal path to hit the top mirror, and then another diagonal path to hit the bottom mirror as the ship moves forward. It's like throwing a ball straight up in a moving car. For someone outside the car, the ball traces a parabolic arc. Crucially, according to Einstein's second postulate, the speed of light must be the same for you on the ground and for the observer on the spaceship. But since your perspective shows the light pulse traveling a longer, diagonal path, and its speed remains constant, the only way for it to cover that longer distance is if it takes more time. Therefore, from your stationary perspective, the clock on the moving spaceship is ticking more slowly. The ticks are further apart. Time itself is dilating or stretching out for the moving object. This isn't just an illusion. It's a real physical effect. If that spaceship returned to Earth after a long, fast journey, the clocks on board would genuinely show less elapsed time than identical clocks that stayed on Earth. Real-world confirmations of time dilation are abundant. Muon decay. Muons are tiny subatomic particles created high in Earth's atmosphere by cosmic rays. They have a very short natural lifespan, about 2.2 microseconds, before they decay. If special relativity weren't real, very few muons created in the upper atmosphere would ever reach the ground. However, far more muons reach us than classical physics predicts. Why? Because from our perspective on Earth, the muons are moving so fast that their internal clock, their rate of decay, slows down. Their lifespan is stretched out, allowing them to travel much farther than they could if time were absolute. Atomic clocks on airplanes. Groundbreaking experiments in the 1970s, like the Hayfel-Keating experiment, flew incredibly precise atomic clocks around the world on commercial airliners. Upon their return, these clocks showed fractions of a second difference compared to stationary clocks on Earth, precisely matching the tiny predictions of special relativity. Though general relativity also plays a role due to gravity, which we'll discuss later. GPS satellites, perhaps the most ubiquitous application of time dilation. GPS satellites orbit Earth at speeds of about 8,700 miles per hour, 14,000 kilometers per hour. Their clocks tick ever so slightly slower than clocks on Earth due to their speed. If these relativistic effects were not accounted for, GPS systems would quickly accumulate errors of many miles per day, rendering them useless. The second astonishing consequence is length contraction. Moving objects appear shorter in their direction of motion. Just as time stretches, space compresses. If an object is moving past you at a very high speed, you would measure its length in the direction of its motion as being shorter than its length when it is at rest. This isn't because the object is physically squashed by some force, but because space itself is effectively compressed from your perspective to maintain the constancy of the speed of light. If you were on the moving object, you would measure your own length as normal, and you would observe our stationary objects as being contracted. Think back to the muon example. From the muon's perspective, its lifespan hasn't changed, but instead of its time dilating, the distance between the upper atmosphere and the Earth's surface has contracted, allowing it to cover the journey within its normal short lifetime. Both time dilation and length contraction are two sides of the same relativistic coin, ensuring that the speed of light remains constant for all observers. Finally, there's the equally mind-bending relativity of simultaneity. Events that appear simultaneous to one observer may not appear simultaneous to another observer who is moving relative to the first. Imagine our fast-moving train again. Lightning strikes simultaneously at both the front and back of the train from the perspective of an observer standing on the ground, midpoint between the strikes. However, for someone on the train, who is moving towards the front strike and away from the rear strike, the light from the front will reach them sooner. Therefore, the person on the train will conclude that the lightning strike at the front happened before the strike at the back. There is no universal now. Whether two events happen at the same time depends entirely on the observer's state of motion. These are not intuitive ideas. Our human experience is confined to speeds vastly slower than light, where relativistic effects are negligible. That's why Newton's laws worked so well for so long. They are an excellent approximation for everyday speeds. But as we approach the cosmic speed limit, the universe reveals itself to be a much stranger and more flexible place. It's a universe where time and space are not absolute stages for events, but rather dynamic participants that warp and bend, ensuring that one fundamental truth, the constancy of light's speed, remains inviolable. The ultimate consequence of this interconnectedness, as we'll see, is the direct relationship between mass and energy. E equals mc2, the universe's signature equation. Of all the profound insights gifted to us by Albert Einstein, one equation stands above the rest. Iconic and instantly recognizable even to those with no background in physics. E equals mc2. It's probably the most famous equation in the world, yet its full meaning and impact are often misunderstood. It's far more than a formula for nuclear bombs. It represents a fundamental truth about the very fabric of existence, revealing a profound unity between mass and energy. To understand E equals mc2, let's break it down. E stands for energy. M stands for mass. C stands for the speed of light in a vacuum, which we've already established as a universal constant. Approximately 186,282 miles per second, or 300,000 kilometers per second. C2 means the speed of light multiplied by itself. This term is crucial because C is an enormous number, and C2 is therefore a staggeringly huge number. The equation tells us that energy E is equal to mass m multiplied by a very large number, C2. What does this mean? It signifies that mass and energy are fundamentally interchangeable. They are not distinct entities, but rather different forms or manifestations of the same thing. Mass can be converted into energy, and energy can be converted into mass. Before Einstein, mass and energy were considered separate, conserved quantities. You could create energy from various sources, and you could move mass around, but you couldn't create or destroy either of them. E equals mc2 showed that, in fact, mass is a form of stored energy, and energy has mass. Think of it this way. Even a tiny amount of mass contains an immense amount of energy, because it's multiplied by the speed of light squared. This explains why nuclear reactions, which involve converting a very small amount of mass into energy, can release such colossal amounts of power. Take the sun, for example. Our sun, the radiant heart of our solar system, is a giant nuclear fusion reactor. Deep within its core, hydrogen atoms fuse to form helium atoms. When this happens, the mass of the newly formed helium atom is ever so slightly less than the combined mass of the hydrogen atoms that went into it. That minuscule amount of missing mass isn't gone. It's converted into a tremendous burst of energy, primarily in the form of light and heat, according to E equals mc2. This ongoing process fuels the sun and powers all life on Earth. The sun converts about 4 million tons of its mass into energy every single second. Yet this is such a tiny fraction of its total mass that it can continue burning for billions of years. On Earth, the most often cited and most devastating example of E equals mc2 in action is the atomic bomb. In an atomic explosion, a small amount of heavy atomic nuclei, like uranium or plutonium, undergo fission, splitting into lighter nuclei. Again, the total mass of the resulting fragments is slightly less than the original mass of the parent nucleus. That difference in mass is instantly transformed into a devastating amount of energy, leading to the destructive power of nuclear weapons. Similarly, nuclear power plants harness this very same principle to generate electricity in a controlled manner. The equation also explains why nothing with mass can reach the speed of light. As an object accelerates, its kinetic energy increases. According to E equals mc2, this increased energy manifests as an increase in the object's relativistic mass. The closer an object gets to the speed of light, the more its effective mass increases, making it harder and harder to accelerate further. To reach the speed of light, an object with mass would require an infinite amount of energy to accelerate its mass, which would become infinitely large. This is an impossibility, reinforcing c as the universe's ultimate speed limit. Only massless particles, like photons, particles of light, can travel at the speed of light. E equals mc2 isn't just about explosions and stars. It's a profound statement about the nature of reality. It tells us that what we perceive as solid, tangible mass is actually a highly concentrated form of energy. And energy, in turn, has a form of mass, contributing to the gravitational field, a concept we'll explore more deeply with general relativity. It unifies two seemingly disparate concepts into a single, elegant truth, demonstrating the astonishing interconnectedness of the universe at its most fundamental level. It's a testament to Einstein's genius that he could distill such a profound realization into just 3 symbols. This mass-energy equivalence, along with time dilation and length contraction, showed that space and time were not independent entities, but rather dynamically intertwined. This realization set the stage for one of Einstein's crucial collaborators to formulate the concept of spacetime. Spacetime, where space and time intertwine. We've explored how special relativity revealed that time can stretch and shrink, and lengths can contract, all to ensure that the speed of light remains constant for every observer. Yet, even with these astonishing revelations about the flexibility of time and space, they were still largely considered as separate entities interacting with each other. It took a clever mathematician, Hermann Minkowski, one of Einstein's former teachers, to formalize what Einstein's theory truly implied. Space and time are not separate, but are inextricably interwoven into a single, unified, 4-dimensional fabric. In 1908, Minkowski famously declared, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This profound statement laid the foundation for the concept of spacetime. Think of it this way: to describe an event in the universe, you need to specify not just where it happened, its 3 spatial coordinates length, width, and height, but also when it happened, its time coordinate. For example, if you want to meet a friend, you state a location, e.g., the coffee shop down the street, and a time, e.g., at 3 p.m. You can't separate the where from the when of the meeting. In our everyday lives, we intuitively treat space and time as distinct, but Einstein and Minkowski showed they are 2 facets of the same underlying reality. Imagine a simple analogy. If you live on a flat piece of paper, you need 2 coordinates, x and y, to locate anything. But if that paper were to become a deformable, single entity, rather than just a backdrop, then moving in x might affect your perception of y, and vice versa. Spacetime takes our 3 familiar spatial dimensions and adds time as a 4th dimension. Every event, every particle, every moment exists within this 4-dimensional continuum. When you move through space, you are also moving through time, and your speed in one dimension can affect your speed in the others. The faster you move through space, the slower you necessarily move through time. This is the essence of time dilation, reinterpreted within the spacetime framework. Within this spacetime, the path of any object is called its world line. If you are sitting perfectly still, your world line is a straight line upwards through time. If you start moving through space, your world line curves, indicating your journey through both space and time. Even light, traveling at c, traces a world line. The speed of light is not just a speed limit in space, but a fundamental speed limit through spacetime. This concept of world lines helps define what is causally connected to us. Picture a light cone. From any point in spacetime, called an event, a double cone can be drawn. The upper cone represents all the possible future events that can be influenced by the initial event, limited by the speed of light. The lower cone represents all the past events that could have influenced the initial event. Everything outside these light cones is causally disconnected. It's too far away in space or time for any information or influence, traveling at or below the speed of light, to have reached or been reached by the event. This concept beautifully illustrates the relativity of simultaneity. Observers in different inertial frames will have different slices of simultaneity through spacetime, but they will always agree on what's inside and outside their light cones. The beauty of the spacetime concept is its elegance. It's not just a mathematical abstraction, it's a profound redefinition of our reality. It provides a natural arena for the phenomena of special relativity, where the bending of time and space ensures the laws of physics are consistent for all observers. But Minkowski's spacetime continuum wasn't just a powerful reinterpretation of special relativity. It was the crucial conceptual leap that paved the way for Einstein's greatest triumph. Special relativity was limited to non-accelerating, or inertial, frames of reference. It didn't account for gravity, the fundamental force that governs the large-scale structure of the universe. Einstein realized that if mass and energy could deform spacetime, then gravity, too, must be intimately connected to how this cosmic fabric behaves. The next and most monumental step was to curve this flat spacetime, giving birth to general relativity. Gravity reimagined, curves in the cosmic fabric. Special relativity, as we've seen, brilliantly unified space and time into spacetime, and revealed mind-bending consequences like time dilation and length contraction. It explained what happens when objects move at constant, high velocities. However, there was a glaring omission. Special relativity did not include gravity. It was a theory of space, time, and motion, but it assumed a flat, unchanging spacetime background. Yet, gravity is the dominant force shaping our universe, from the orbit of planets to the formation of galaxies. Einstein knew his work wasn't complete without incorporating it. For Newton, gravity was a mysterious, invisible force of attraction between any two objects with mass. It acted instantaneously across vast distances, a concept Newton himself found unsettling but couldn't explain. Einstein, with his deep understanding of fields and his insistence on finite signal propagation speeds, like the speed of light, found this instantaneous action problematic. He sought a more fundamental explanation. The breakthrough, which Einstein later called his happiest thought, came in 1907. He imagined a man falling from a roof. The man, in freefall, would not feel his own weight. He would experience weightlessness, just as an astronaut does orbiting Earth. This simple realization led to the cornerstone of general relativity, the equivalence principle. The equivalence principle states that there is no experiment a person can perform locally to distinguish between the effects of a uniform gravitational field and the effects of uniform acceleration. To illustrate this, consider the famous Einstein's elevator thought experiment. Scenario 1. You are in an elevator car out in the vacuum of space, far away from any planets or stars. The elevator is being constantly accelerated upwards by an unseen rocket engine. If you drop a ball, it will accelerate downwards towards the floor due to the elevator's upward acceleration, hitting the floor and appearing to have weight. If you shine a flashlight horizontally across the elevator car, the light ray will appear to bend downwards slightly as the floor accelerates up to meet it. Scenario 2. You are in an identical elevator car, sitting motionless on the surface of Earth. You drop the same ball, and it falls to the floor due to Earth's gravity. When you shine your flashlight horizontally, the light ray appears to travel in a straight line. Now, here's the crucial insight. If you were inside either elevator, without any outside information, you could not tell which scenario you were in. The ball would behave identically, and the light would appear to travel the same bent path. Though the bending due to gravity on Earth is too small to notice in an elevator, it's theoretically there. Gravitational effects are locally indistinguishable from acceleration effects. This thought experiment revealed a profound truth. If acceleration can bend light, as it must in the accelerating elevator, and if gravity is equivalent to acceleration, then gravity must also bend light. But how could gravity, a force, bend light, which is massless? Einstein's revolutionary answer was that gravity is not a force pulling objects through space. Instead, gravity is a manifestation of the curvature of spacetime itself, caused by the presence of mass and energy. Imagine a large, stretched rubber sheet. Now, place a heavy bowling ball in the center of the sheet. The bowling ball creates a dip or depression in the sheet. This is analogous to a massive object, like a star or planet, curving the fabric of spacetime around it. Now, roll a small marble gently across the surface of the rubber sheet. As the marble approaches the bowling ball, it doesn't get pulled, by a direct force from the bowling ball. Instead, it follows the curve in the sheet created by the bowling ball. Its path is deflected as it rolls into the dip, making it orbit the bowling ball or spiral towards it. This is analogous to how planets orbit stars. The Earth isn't being pulled by the sun's gravity as a force across empty space. Rather, the sun's immense mass has curved the fabric of spacetime, and Earth is simply following the straightest possible path within that curved geometry. These straightest possible paths in curved spacetime are called geodesics. Just as a great circle, like the equator, is the straightest path on the curved surface of Earth, a geodesic is the straightest path in curved spacetime. Objects, even light, simply follow these geodesics. What we perceive as gravity, the pull of celestial bodies, is actually merely objects responding to the geometry of spacetime that massive objects have distorted. This seemingly abstract idea had immediate and testable consequences. If spacetime is curved by mass, then light, which always follows the straightest path, should also be affected by this curvature. This means starlight passing near a massive object like the sun should appear to bend. This was a radical prediction, and its confirmation would catapult Einstein from a respected physicist to a global icon. Bending light and warping time. Einstein's general theory of relativity, with its radical premise that gravity is not a force, but a manifestation of curved spacetime, was a truly audacious proposal. For such a revolutionary idea to gain acceptance, it needed more than elegant mathematics and insightful thought experiments. It required concrete, testable predictions that could be verified through observation. Fortunately, general relativity delivered, and its predictions have been spectacularly confirmed, cementing its place as one of the most successful scientific theories ever conceived. The first, and arguably most dramatic, prediction of general relativity was that light would bend in the presence of strong gravitational fields. If massive objects curve spacetime, and light always follows the straightest possible path, a geodesic, within that curved fabric, then light rays passing near a large mass should appear to be deflected. For centuries, light was thought to travel exclusively in straight lines. Newton's theory suggested light might bend slightly due to the sun's gravity, through a purely particle-based interaction, but Einstein's theory predicted an effect twice as large. The ideal object for testing this was our sun. Its immense mass would create a significant curvature in spacetime. The challenge, however, was that the sun is so bright it usually makes observing distant starlight impossible. The perfect opportunity arose during a total solar eclipse. In 1919, British astronomer Arthur Eddington, a devout pacifist, led an expedition to Principe Island off the coast of West Africa during a total solar eclipse. His team photographed the stars located near the sun's limb, stars whose light was passing close to the sun on its way to Earth. During the eclipse, the sun's blinding disk was briefly obscured, allowing the faint starlight to be captured. These photographs were then compared to images of the same stars taken months earlier, when the sun was in a different part of the sky and its gravitational influence on their light would not be a factor. The results were electrifying. The stars appeared to be slightly shifted from their usual positions, and the amount of the shift perfectly matched Einstein's predictions. When the news reached the world, it caused a sensation. The New York Times famously declared, "Lights all askew in the heavens, Einstein's theory triumphs." Einstein went from a respected, albeit niche, physicist to a global celebrity overnight. This confirmation marked a turning point, solidifying general relativity's standing and irrevocably changing our understanding of gravity. Today, this phenomenon, known as gravitational lensing, has been observed countless times with distant galaxies and galaxy clusters bending the light from even more distant objects, creating distorted, magnified, or multiple images of them. These cosmic lenses are powerful tools for astronomers, allowing them to study dark matter and the early universe. Another triumph for general relativity was its accurate explanation of the anomalous perihelion precession of Mercury. Mercury, the planet closest to the Sun, has a highly elliptical orbit. Over time, the point in its orbit closest to the Sun, its perihelion slowly shifts or precesses. While most of this precession could be explained by the gravitational influence of other planets using Newton's laws, there was a tiny, stubborn discrepancy of about 43 arcseconds per century. An arcsecond is an extremely small angle, 13600 of a degree, that Newtonian mechanics simply could not account for. It was a persistent puzzle for astronomers. Einstein's general relativity, however, naturally explained this missing 43 arcseconds as a direct consequence of the Sun's immense mass curving spacetime around it. Mercury was simply following the curved geodesics around the Sun, and this curvature precisely accounted for the anomalous precession. A third prediction was gravitational redshift. If light loses energy as it climbs out of a gravitational well, think of it like a ball losing speed as it rolls uphill. Then its frequency should decrease, and its wavelength should get longer, shifting it towards the red end of the spectrum. This effect is minuscule on Earth, but was famously confirmed in 1959 by the Poundribka experiment, which measured the tiny frequency shift of gamma rays moving between the top and bottom of a 74-foot tower at Harvard University. It's also observed in light from distant stars and galaxies, where light struggling to escape the intense gravity of massive stars or black holes is visibly redshifted. Perhaps the most monumental recent confirmation of general relativity came in 2015, with the direct detection of gravitational waves. Just like a pebble dropped into a pond creates ripples on the surface, massive accelerating objects in spacetime, particularly incredibly energetic cosmic events like the collision of black holes or neutron stars, generate ripples in spacetime itself. These ripples, gravitational waves, travel at the speed of light, carrying energy away from their source. Einstein predicted gravitational waves in 1916, but he doubted they would ever be detectable due to their incredibly tiny amplitude. For decades, the only evidence was indirect. In 1974, astronomers Joseph Taylor and Russell Hulse observed a binary pulsar, two neutron stars orbiting each other, and found that their orbital period was gradually speeding up, indicating that they were losing energy, precisely at the rate predicted by general relativity through the emission of gravitational waves. This work earned them the Nobel Prize in Physics in 1993. The direct detection came nearly a century after Einstein's prediction, thanks to two colossal instruments, the Laser Interferometer Gravitational Wave Observatory, or LIGO, located in two separate facilities in Washington and Louisiana. Each LIGO detector consists of two arms, each 4 kilometers long, arranged in an L shape. Lasers are bounced back and forth along these arms. When a gravitational wave passes through Earth, it momentarily stretches and squeezes spacetime itself, causing the arms of the interferometer to lengthen and shorten by an infinitesimal amount, less than 1/10,000th the diameter of a proton. LIGO detected these ripples, confirming the existence of gravitational waves and opening up a completely new window to observe the universe. These confirmations, spanning a century of scientific effort, collectively demonstrate the profound accuracy of general relativity. It is a theory that not only describes gravity with unparalleled precision, but also leads to some of the universe's most extreme and fascinating phenomena, which we will explore next. Monsters of gravity. Black holes and wormholes. Einstein's general theory of relativity describes gravity as the curvature of spacetime caused by mass and energy. When we look at everyday objects or even planets orbiting stars, this curvature is gentle, like a slight dip on our cosmic rubber sheet. But what happens when the mass within a given region becomes extraordinarily concentrated? What happens when the curvature becomes so extreme that it creates a cosmic abyss from which nothing, not even light, can escape? This is where we encounter some of the most mind-bending entities predicted by general relativity: black holes. A black hole is not a hole in the traditional sense, nor is it merely a vacuum cleaner of the cosmos. It is a region of spacetime where gravity is so incredibly intense that anything, matter, light, radiation, that ventures too close is trapped forever. This extreme gravity is caused by an immense mass being squeezed into an incredibly small volume. The defining feature of a black hole is its event horizon. This is not a physical boundary, but rather a point of no return. Once something crosses the event horizon, it would need to travel faster than the speed of light to escape the black hole's gravitational pull, which, as special relativity tells us, is impossible. For an outside observer, Anything that falls into a black hole appears to slow down as it approaches the event horizon, its light becoming redshifted until it effectively freezes and fades from view, never quite crossing the boundary. For the infalling object, however, passage through the event horizon occurs in a finite, perhaps unremarkable, amount of its own time. Beneath the event horizon, general relativity predicts that all the mass of the black hole collapses down to an infinitely dense point called a singularity. Here, the laws of physics as we currently understand them break down. What truly exists at the singularity remains one of the greatest mysteries in physics, a frontier where quantum mechanics and general relativity clash. Black holes are thought to form in several ways. Stellar mass black holes. These are born from the collapse of very massive stars, typically those more than 20 to 30 times the mass of our Sun. When such a star exhausts its nuclear fuel, its core can no longer withstand the crushing force of its own gravity and collapses inward. If the remaining core is sufficiently massive, it will continue to collapse past the point of forming a neutron star until it becomes a black hole. Supermassive black holes. These behemoths, millions or even billions of times the mass of the Sun, reside at the centers of most large galaxies, including our own Milky Way, where Sagittarius A lurks. Their formation is still a subject of active research, but they are thought to grow by accreting gas and dust, and by merging with other black holes. For a long time, black holes were purely theoretical curiosities, abstract solutions to Einstein's equations first explored by Carl Schwarzschild during World War I. However, in recent decades, observational evidence for their existence has become overwhelming. Indirect detection. Astronomers have observed stars orbiting unseen, supermassive objects at galactic centers at astonishing speeds, consistent only with the presence of a black hole. Likewise, X-ray binaries, systems where a normal star orbits a black hole, emit X-rays as gas from the normal star is heated to extreme temperatures while spiraling into the black hole. Direct imaging. In 2019, the Event Horizon Telescope, EHT, collaboration made history by releasing the first-ever image of a black hole's shadow, a dark region surrounded by a bright ring of emission, at the center of the galaxy Messier 87. This was followed by an image of Sagittarius A in 2022. While we can't image the black hole itself, we can image the warped, superheated gas and light just outside its event horizon. Gravitational waves. As discussed in the previous chapter, LIGO and Virgo have directly detected gravitational waves primarily from the mergers of black holes, offering compelling evidence of their existence and the violent nature of their interactions. Just as a light clock in motion experiences time dilation, objects closer to a massive body, deeper in its gravitational well, also experience time dilation. For instance, clocks on Earth run ever so slightly slower than clocks in space, an effect that, combined with the special relativistic effect, our GPS systems must account for to function accurately. The closer you get to a black hole, the more extreme this gravitational time dilation becomes. Theoretically, if you could orbit just outside a black hole's event horizon, you could witness the entire future history of the universe unfold in a fraction of your own personal time. Another fascinating, though highly speculative, theoretical consequence of general relativity are wormholes. Sometimes called Einstein-Rosen bridges, wormholes are hypothesized tunnels through spacetime that could connect two distinct points in spacetime. Imagine you have a sheet of paper with 2 points far apart. A wormhole would be like folding the paper and punching a hole through it, allowing you to travel between the points much faster than by traversing the surface. While mathematically possible solutions to Einstein's equations, theoretical wormholes are incredibly unstable and would likely collapse instantly unless held open by exotic matter with negative energy density, something that has not been observed and may not even exist. For now, wormholes remain largely the domain of science fiction, an intriguing concept that highlights the bizarre possibilities inherent in a highly warped spacetime. From the crushing densities of singularities to the theoretical shortcuts of wormholes, black holes and their kin represent the most extreme predictions of Einstein's general relativity. They are cosmic laboratories where the fabric of reality is stretched to its breaking point, pushing our understanding of the universe to its very limits. And crucially, these behemoths of gravity play a critical role in the evolution of galaxies and the larger cosmos, leading us to our next exploration. The universe's grand story. Einstein's general relativity didn't just revolutionize our understanding of gravity on a local scale, explaining the orbits of planets and the bending of starlight. It provided the ultimate framework for understanding the universe on its grandest scale, its origin, evolution, and ultimate fate. It became the cornerstone of modern cosmology, the study of the universe as a whole. When Einstein first applied his field equations of general relativity to the entire universe in 1917, he made a startling discovery. His equations predicted that the universe must either be expanding or contracting. They did not allow for a static, unchanging universe, which was the prevailing belief at the time. This troubled Einstein, as he, along with most scientists, assumed the universe was eternal and immutable. To force his equations to produce a static universe, he reluctantly introduced a term called the cosmological constant, lambda, a fudge factor representing a repulsive force that would counterbalance gravity and hold the universe in a steady state. He would later call this his biggest blunder. Meanwhile, observational astronomy was making rapid progress. In the 1920s, American astronomer Edwin Hubble, working at Mount Wilson Observatory, made a series of pivotal observations. By studying distant galaxies, he discovered that, with very few exceptions, all galaxies are moving away from us, and the farther away they are, the faster they are receding. This phenomenon, known as Hubble's law, was a direct confirmation of the expanding universe predicted by Einstein's equations. The universe wasn't static. It was dynamic, stretching and growing like rising dough with raisins embedded in it. The raisins, galaxies, move further apart as the dough expands, but they themselves don't expand. Hubble's discovery of the expanding universe was a monumental turning point. It suggested a radical idea. If the universe is expanding today, then in the past, it must have been smaller, denser, and hotter. Tracing this expansion backward in time, it leads inevitably to a moment when all the matter and energy in the universe were compressed into an unimaginably hot and dense state, the event we now call the Big Bang. The Big Bang theory is not an explosion out into space, but rather an expansion of space itself. It's the prevailing cosmological model for the observable universe, and general relativity provides the mathematical backbone for describing its evolution. But the Big Bang was more than just a theoretical prediction. It was soon bolstered by one of the strongest pieces of evidence in all of cosmology, the cosmic microwave background, CMB, radiation. In 1964, Arno Penzias and Robert Wilson, two engineers at Bell Labs, stumbled upon a persistent, faint microwave hiss coming from every direction in the sky. It wasn't localized, it was uniform. This accidental discovery turned out to be the faint afterglow of the Big Bang itself. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine, forming neutral atoms. This made the universe transparent, allowing photons to travel freely. These photons, now stretched into microwaves by billions of years of cosmic expansion, are the CMB, providing a snapshot of the universe when it was just an infant, incredibly uniform and hot. The Big Bang model, built upon general relativity and supported by observations like Hubble's expansion and the CMB, paints a grand narrative of cosmic evolution. From a hot, dense singularity, the universe expanded, cooled, and formed the first particles, then light chemical elements, and eventually stars and galaxies. Gravity, as described by general relativity, then sculpted these structures over billions of years, pulling matter together to form the intricate cosmic web we observe today. However, as cosmology advanced, two new mysteries emerged from observations, challenging our current understanding, even within the framework of general relativity: dark matter. When astronomers measured the rotation speeds of galaxies and the clustering of galaxies in galaxy clusters, they found that the observed matter, stars, gas, dust, simply wasn't enough to provide the gravitational pull needed to hold these structures together. It appeared that an additional, invisible form of matter, dubbed dark matter, must be present. Dark matter doesn't interact with light or other electromagnetic radiation, making it invisible to our telescopes, but its gravitational effects on visible matter are clear. It's estimated to make up about 27% of the universe's total mass energy content. Dark energy. In the late 1990s, observations of distant supernovae revealed another astonishing truth. The expansion of the universe isn't slowing down due to gravity, as was expected. It's actually accelerating. This implies the existence of a mysterious force or energy inherent in space itself, pushing galaxies apart. This enigmatic component is called dark energy, and it's the largest constituent of our universe, estimated to make up about 68% of its total mass energy. Interestingly, Einstein's biggest blunder, the cosmological constant, has made a surprising comeback as one of the leading candidates for dark energy. General relativity provides the equations that describe how dark matter and dark energy influence the universe's expansion and structure formation, even if their fundamental nature remains unknown. The universe's grand story, shaped by gravity and spacetime, continues to unfold, revealing new puzzles even as it solves old ones. From the smallest curvature around a star to the largest structures in the cosmos, Einstein's theory of relativity has fundamentally reshaped our understanding of reality. It's a testament to its power that it describes everything from the GPS signal on your smartphone to the vast history of the universe itself. But is the story complete? As we will see in our final chapter, Einstein's legacy continues to inspire and inform the quest for a unified theory of everything. Einstein's enduring legacy. We have journeyed from a curious young patent clerk, pondering light beams, to the awe-inspiring depths of black holes and the mysteries of cosmic expansion. Einstein's theories of relativity, both special and general, have not merely added new facts to our scientific understanding. They have profoundly reshaped our very perception of space, time, gravity, and the universe. His legacy is not just a collection of equations, but a transformed worldview. At its core, relativity taught us that the universe is not a static, mechanical machine with absolute coordinates. Instead, it is a dynamic, interconnected fabric where space and time are inextricably linked, flexible, and influenced by matter and energy. This wasn't just a philosophical shift. It had tangible, practical consequences that are felt every day. Perhaps the most familiar practical application of relativity is your global positioning system, GPS. When you navigate with your smartphone, you are directly experiencing the predictions of Einstein's theories. GPS satellites orbit Earth at speeds of about 8,700 miles per hour, and they are also in a weaker gravitational field than us on the surface. Due to special relativity's time dilation, the clocks on these fast-moving satellites tick slightly slower than clocks on Earth. But also, due to general relativity's gravitational time dilation, clocks tick faster in weaker gravity, their clocks tick slightly faster than clocks on Earth. The general relativistic effect is larger, so overall atomic clocks aboard GPS satellites run about 38 microseconds, millionths of a second, faster per day compared to clocks on Earth. While this may seem like an infinitesimally small amount, if these relativistic corrections were not factored into the GPS calculations, your navigation system would accumulate errors of several miles per day, rendering it useless. Without Einstein, your journey to the local coffee shop would be a much more perplexing adventure. Beyond GPS, relativity continues to be a vibrant field of research. The direct detection of gravitational waves by projects like LIGO and Virgo has opened an entirely new window onto the universe, allowing us to hear the violent cosmic symphony of merging black holes and colliding neutron stars. This new field of gravitational wave astronomy promises to reveal phenomena we couldn't even imagine with traditional light-based telescopes, offering fresh insights into black holes, the early universe, and even exotic objects we have yet to discover. Scientists are also constantly testing general relativity in extreme environments, such as near neutron stars and black holes, to see if it holds up under the most intense conditions. So far, it has passed every test with flying colors. However, Einstein's grand symphony remains unfinished. While general relativity describes the universe on the grandest scales: planets, stars, galaxies, and the cosmos, It has a fundamental incompatibility with quantum mechanics, the theory that governs the universe at the smallest scales, atoms, particles, and fundamental forces, excluding gravity. General relativity is a continuous, smooth description of spacetime, while quantum mechanics describes the universe as granular and probabilistic. These two pillars of modern physics, incredibly successful in their respective domains, simply do not work together. The quest for a unified theory of quantum gravity, a single, coherent framework that seamlessly integrates general relativity and quantum mechanics, is the holy grail of modern physics. Theories like string theory and loop quantum gravity are ambitious attempts to bridge this divide, proposing that at the most fundamental level, space and time themselves might be quantized or discrete rather than continuous. Unifying gravity with the other three fundamental forces, electromagnetic, strong nuclear, and weak nuclear, would represent the ultimate triumph of physics, allowing us to understand phenomena like the very first moments of the Big Bang, where both gravity and quantum effects were supremely important. On a deeper, philosophical level, Einstein's work redefined our understanding of reality. It moved us beyond a static, Newtonian universe to one that is profoundly dynamic and relational. It highlighted causality, the idea that events are connected and must be within the speed of light from each other. It taught us humility, showing how our intuitive, everyday experiences of space and time are merely approximations of a far more complex and beautiful reality. Time and space are not external containers, but integral components of the events within them. Beyond his scientific achievements, Albert Einstein remains an enduring human icon. He was a brilliant but independent thinker, often challenging dogma. He was a pacifist, a humanitarian, and a deep believer in the power of curiosity and imagination. His personal struggles, his triumphs, and his profound insights continue to inspire generations of scientists and laypeople alike. The fabric of reality has revealed itself to be far more intricate and wondrous than imagined before Einstein. From the subtle bending of light to the colossal collisions of black holes, his theories provide the lens through which we view the cosmos. And as the universe continues to reveal its secrets, equipped with new tools and deepening insights, we continue to walk the path Einstein paved, forever bound by the fundamental principles he unveiled in the very fabric of reality.